All right, let's talk about logistic models now, logistic growth models. So a logistic growth model is more of a realistic model for population growth because what we normally see is, and again, exponential growth models is fine for certain particular situations, like for example at the beginning of a growth phase, or when a species or an animal or some creature is introduced to a new habitat where there aren't maybe there aren't predators and there's lots of resources and food and whatnot, then you'll definitely see exponential growth. But does exponential growth happen over infinity? No, because again, habitats are finite, right? You have a finite number of resources, water, you've got predators most likely to deal with, right? And so all of those factors, right? Death rates, right? So all those factors contribute to the fact that exponential growth in the real world can't happen forever, okay? So a logistic growth model is a more realistic because it takes into consideration that, hey, the growth rate doesn't stay the same. Like in an exponential function, we assume that the growth rate is constant, right? But in a logistic growth model, the growth rate is changing based on the size of the population. So here's what the logistic growth model looks like, okay? So a logistic growth model is a function written in the form of y equals c divided by this whole thing here, which is 1 plus a times e to the negative bt power. So we've got this exponential decay function going on here, times a coefficient, and then we've got this other constant here. So constants a, b, and c are positive. So that's the other thing. These are all positive constants, right? So we've got this decay function here. So where's this going? As time goes on, this is going towards what? This is getting smaller and smaller and smaller, which is going towards what? 0. So what's happening to the population size? Y? Well, as this goes towards 0, this is going towards C. So Y is heading towards C. C is what we call the carrying capacity of the habitat. C will change depending on the situation, depending on the habitat, resources, all kinds of things, okay? So the carrying capacity is the maximum amount of the growth, the maximum number of things, right? Creatures, bacteria, animals, whatever, humans. The carrying capacity is the maximum amount that the habitat will be able to sustain indefinitely. And so you'll see in growth models, like logistic growth models, they start out looking exponential, right? So let's say we have here, this is our C value, so this is our carrying capacity. So we've got this line here, that's the carrying capacity. And so in the beginning, when we introduce the population, it will grow like exponential, right? It'll start to curve up exponential, and then it gets to the point where there's an inflection point where it becomes concave, from concave up to concave down, and the growth slows down, right? Starts to slow down. So at this point here, it'll start to slow down, and it'll reach or get towards the carrying capacity. So it has this S growth, or what we call an S curve, okay, which is common in lots of different disciplines. So, yeah, that's the logistic growth model.